Previously, we solved the time-independent Schrödinger equation for the particle in a one-dimensional box problem. In this lesson, we will use the solutions to illustrate several important concepts in quantum mechanics. For brevity, we will frequently be referring to the particle as the PIB. When we solved the time-independent Schrödinger equation for the PIB, we found the wave functions to be given by psi equals square root of 2 over L times the sine of n pi x over L, and that the allowed energies are equal to n squared pi squared h bar squared over 2ml squared, or n squared h squared over 8ml squared. Just as a reminder, h is Planck's constant, h bar is Planck's constant over 2 pi, m is the mass of the particle, and L is the length of the box. We saw that n in these formulas naturally came out of the mathematics when we applied the boundary conditions to the general solution of the Schrödinger equation. We found that n is restricted to non-zero integers, and for our complete set of solutions to the Schrödinger equation, we chose just the positive numbers. We refer to n as a quantum number. For the PIB, it's convenient to put n as a subscript for E and psi so that we can easily refer to the different allowed energies and the wave functions associated with these energies. We say that each allowed value of n represents a quantum state of the system that is described by psi sub n. The quantum state with the lowest energy is called the ground state. So the term ground state energy refers to the lowest allowed energy of the system. The lowest value for E is when quantum number n is equal to 1. So the ground state energy is E sub 1. Substituting 1 for n in the formula for E sub n, we get E sub 1 equals pi squared h bar squared over 2 ml squared, or h squared over 8ml squared. The ground state energy is also known as the 0-point energy. Is the ground state energy of a PIB equal to 0? Obviously not, so don't take the phrase 0 point literally. The wave function that is associated with the ground state energy is called the ground state wave function. For the PIB, this would be psi sub 1, which is equal to the square root of 2 over L times the sine of pi x over L. The term excited state refers to a state with an energy higher than that of the ground state. For the PIB, the first excited state is the quantum state with n equals 2. The first excited state wave function is psi sub 2, or square root of 2 over L times the sine of 2 pi x over L. The energy of the first excited state is E sub 2. Plugging in 2 for n in the expression for E gives us 4 pi squared h bar squared over 2ml squared, or 4h squared over 8ml squared. It's easy to see that this is just equal to 4 times E sub 1, where E sub 1 is the ground state energy. Note that in general, E sub n is just equal to n squared times E sub 1. What is the energy of the third excited state of a PIB? For the first excited state, n equals 2. For the second excited state, n is equal to 3. For the third excited state, n is equal to 4. Therefore, the energy of the third excited state is 4 squared times E1, or 16 times the ground state energy. An energy level diagram is useful for visualizing the quantization of energy. For the PIB, the energy level diagram would look something like this. Note that for the ground state, where n equals 1, the energy is not 0. The energy of the first excited state, n equals 2, is 4 times that of the ground state. The energy of the second excited state, n equals 3, is 9 times that of the ground state. It should be obvious from this diagram that the gap between allowed energy levels increases as n increases. For example, the gap between E2 and E1 is 3E1. 4e1 minus e1 is 3e1. The gap between e3 and e2 is bigger. It's 5e1. 9e1 minus 4e1 is 5e1. Just a clarification of what the word quantized means. It means more than just being restricted. A better synonym is discrete, spelled D-I-S-C-R-E-T-E. Do not confuse this with the word which is spelled as D-I-S-C-R-E-E-T, which means low profile or inconspicuous. Quantized or discrete means you can find two allowed values such that nothing between them is allowed. The antonym is continuous. For example, if x is a real number that has to be an integer, it is quantized, it is discrete. A value of 5 is allowed and a value of 6 is also allowed, but anything between 5 and 6 is not allowed. Also note that if x is quantized, anything that depends on x must also be quantized. But if x can be any real number restricted to be less than 100, it is not quantized, even though it is restricted. It is continuous. For example, a value of 5 is allowed and a value of 6 is allowed, but everything between 5 and 6 is also allowed. What if x can only be 1/2 or negative 1/2? Is it quantized? The answer is yes. It is restricted to just these two numbers. Let's take a look now at the plots of the PIB wave functions. Let's start with the ground state. Inside the box, psi for n equals 1 is square root of 2 over L times the sine of pi x over L. Here's what the plot looks like. Note that at x equals 0, psi is 0. If we plug in 0 for x, the sine function is equal to 0, which makes psi equal to 0. We can also see that at x equals L, psi is also 0. If we plug in L for x, the argument for the sine function becomes pi L over L, or pi. Sine of pi is also 0. Note that inside the box, as x goes from 0 to L, the argument in the sine function goes from 0 to pi. That is half of a cycle for a sine function. In other words, we could say that a PIB in the ground state has a de Broglie wavelength of 2L, since the sine function completes a cycle when its argument goes from 0 to 2 pi. We can see that the maximum value of psi occurs in the middle of the box at L over 2. What do you think is the value of psi at this point? If you recall, the range for the sine function is -1 to +1. So the maximum possible value for the sine factor here is 1. This means that the maximum value for psi is square root of 2 over L. Finally, note that outside the box, psi is 0. Our function is continuous and single valued. Let's take a look at the excited states. Here we have plots of the wave functions for n equals 2 and n equals 3, along with a plot of the ground state wave function for comparison. Note that the origins for the plots are different. For the ground state, n equals 1, the scale is set up so that psi is 0 here. For the first excited state, n equals 2, psi is 0 here. And for the second excited state, n equals 3, psi is 0 here. What do these functions have in common? You can see that at the edges of the box and outside, psi is equal to 0. At x less than or equal to 0, psi is 0. And at x greater than or equal to L, psi is also equal to 0. They all have the same maximum value of psi. It's square root of 2 over L, since the maximum possible value for the sine factor is 1. For the excited states, psi can complete at least one cycle, and the minimum occurs at negative square root of 2 over L, as expected, since the minimum value for the sine function is -1. How do the functions differ? One thing you can observe here is that excited states have nodes, A node is a location where the wave function changes sign. Consider the wave function for n equals 2. It has one node, here in the middle of the box, at x equals L over 2. To the left of this location at x less than L over 2, the wave function is positive. To the right of this location, at x greater than L over 2, the wave function is negative. When a function changes from positive to negative, it has to go through 0. So we can say that at a node, the wave function is 0. If we plot several wave functions, we will see a pattern in the number of nodes. Generally, higher energy wave functions will have more nodes. For the wave functions of the particle in a box, the number of nodes is equal to n minus 1. For example, how many nodes are there for the second excited state? For the second excited state, n equals 3, and as shown here, it has two nodes, n minus 1, or 3 minus 1 is equal to 2. Another pattern we can observe for PIB wave functions is that the nodes are evenly spaced inside the box. So for n equals 2, we see the one node is in the middle of the box at L over 2. Where are the nodes located for n equals 3? The two nodes are located at L over 3 and 2L over 3. The nodes divide the box into three sections of equal lengths. We can actually verify all of these by simply setting the expression for the wave function equal to 0 and solving for the x values that would satisfy the equation. We can also see that the crests and troughs in the wave function occur halfway between nodes. Finally, we can show that the de Broglie wavelength is 2L over n. Example, for the first excited state, n equals 2, 2L over n, or 2L over 2, is equal to L. The length of the box is one wavelength. We can see from the plot here that for n equals 2, the wave function completes one cycle from x equals 0 to x equals L. Let's take a look at the probability density functions. The probability density function is obtained by multiplying psi by its complex conjugate, which we can also write as the square of the absolute value of psi. Replacing psi by square root of 2 over L times sine n pi x over L, we get 2 over L times the square of sine n pi x over L. Shown here is a plot of the probability density function for the first excited state, n equals 2. Recall that this function has one node. Here it is at L over 2. We saw earlier that psi is positive at locations to the left of the node and negative at locations to the right. But here we are plotting the square of the absolute value, which is always positive. So instead of dipping below 0, our plot just goes back up as we cross the node. What do you think is the maximum value of the probability density function? Since the minimum and maximum value of the sine function are negative 1 and plus 1, the maximum value of sine squared is 1. Therefore, the maximum value of the probability density function is 2 over L. Based on this plot, what are the most probable locations of the particle? These would be locations where the probability density is at a maximum. Here, halfway between the left edge of the box and the node at x equals L over 4, and here, halfway between the node and the right edge of the box at x equals 3L over 4. Does this agree with classical prediction? The answer is no. Remember that classically we expect the particle to move at constant speed inside the box. If we imagine taking a bunch of random snapshots of the particle, we don't expect it to be more likely that the particle would be at any particular location. It will be equally probable to find it everywhere inside the box. For a one-dimensional system like the PIB, probability density means probability per unit length. If we want actual probability, we have to specify a finite interval. For example, we can calculate the probability of finding the particle between x equals a and x equals b. We simply integrate the probability density with respect to x from x equals a to x equals b. The integral is a number between 0 and 1. If we plot the probability density versus x, the value of the integral corresponds to the area under the curve from x equals a to x equals b, which is the region that is shaded in red here. Shown here are the probability density functions for n equals 1, n equals 2, and n equals 20. What is the probability of finding the particle in the left half of the box? To answer this question, we need to integrate the absolute value of psi squared with respect to x. What integration limit should we specify? Since we are interested in the left half of the box, the lower limit a should be equal to 0, and the upper limit b should be equal to L over 2. We can plug in the expressions for psi and evaluate the integral, but it should be easy to see from the plots that the answer is 1/2. Based on symmetry, we can see that in every case, regardless of what the quantum number n is, the areas under the curve on the right half of the box are equal to the areas on the left half of the box. What is the value of the integral shown here? You can work this out the hard way, but here is a faster way of figuring it out. You should be able to recognize that this function is psi 2 and this function is psi 3, and we are integrating over the entire box. There is a theorem that says that non-degenerate eigenfunctions of a Hermitian operator are orthogonal to each other. This theorem is fairly easy to prove. Therefore, the integral is equal to 0. The wave functions are eigenfunctions of the Hamiltonian operator. The Hamiltonian operator is a Hermitian operator, and psi 2 and psi 3 are eigenfunctions of the Hamiltonian operator, and we know that they have different eigenvalues. Remember that the eigenvalues of the Hamiltonian operator are the allowed energies. Psi 2 and psi 3 represent quantum states with different energies. Here's a nice way to visualize why the integral is 0. Here we have psi 2 and psi 3 plotted separately. And here we have a plot of psi 2 times psi 3. Integration from x equals 0 to x equals L simply means the area under the curve from x equals 0 to x equals L. As you can see, the area shaded in yellow is equal to the area shaded in blue. Since the blue area is below the x-axis, it is considered to be a negative area. The total area is 0. Here's the proof that non-degenerate eigenfunctions of a Hermitian operator are orthogonal to each other. Let operator A be a Hermitian operator with eigenfunctions f and g. We assume that f and g are non-degenerate, which means that their eigenvalues given here as little a and b are not equal. Since a is Hermitian, we can write the following in direct notation. Integral of f star times a hat g over all space is equal to the integral of complex conjugate of a hat f times g over all space. In other words, I can move the a hat operator in front of the function in the bra. Let's simplify the left-hand side. We apply a hat on g. Then, since g is an eigenfunction of a hat with eigenvalue b, we replace a hat g by bg. Since b is a constant, we can pull it out of the integral. Let's simplify the right-hand side. We apply a hat on f. Since f is an eigenfunction of a with eigenvalue little a, we replace a hat f by little a times f. Since little a is a constant, we can pull it out of the integral as a star. Note that little a inside the bra actually means a star. But all eigenvalues of a Hermitian operator are real, so we can replace a star by a. Now, since a and b are not equal, the only way both sides of the equation can be equal is for the integral of f star g over all space to be 0. In other words, f and g are orthogonal. The PIB wave functions that we got from the time-independent Schrödinger equation, which depend only on x, are in fact just part of the overall wave functions called stationary state wave functions. They are called the spatial part and are represented by lowercase psi. We multiplied them by a time-dependent part, which is e to the negative iet over h bar, in order to get the overall function, which we represent by uppercase psi. In an earlier lesson, we learned that stationary states exist if the Hamiltonian operator is independent of time, which is the case for our PIB system. The stationary state wave function itself does depend on time, but they are called stationary states because the probability density does not depend on time. The actual probability density function is big psi star times big psi. It is easy to show that for stationary states, it is equal to little psi star times little psi, which means it does not depend on time. Shown here are animations of the classical motion of a particle in a box, along with animations for 3 stationary states. The red and blue curves represent real and imaginary components of the overall wave function. How would you write the complete stationary state wave function for this one? Since little psi is equal to 0 at the nodes, big psi must also be equal to 0 at the nodes at all times. This function has 2 nodes, so quantum number n for this function is equal to 3. Remember that the number of nodes is equal to n minus 1. 3 minus 1 is 2. Therefore, big psi is equal to the spatial part, square root of 2 over L times sine of 3 pi x over L, times the part that depends on time, e to the negative ie3t over h bar, where e3 is 9h squared over 8ml squared. The real part of big psi is little psi times cosine of e3t over h bar, and the imaginary part of big psi is little psi times sine of e3t over h bar. The Bohr correspondence principle states that quantum mechanics should agree with classical mechanics in cases where classical mechanics is known to be valid. So far, we've seen that the quantum and classical prediction for the particle in a box do not agree. Quantum mechanics predicts that probability of finding the particle inside the box is not uniform, contrary to classical expectation. Let's look at the following problem to illustrate the Bohr correspondence principle. Consider a helium atom in a 1-liter box as a particle in a 1-dimensional box. Kinetic molecular theory, using classical mechanics, successfully explains the behavior of gases. At 300 Kelvin, the theory predicts that the average kinetic energy of a helium atom would be 6.2 times 10 to the negative 21 joules. What is the quantum state of the average helium atom? For a particle in a box, the energy is n squared h squared over 8ml squared. We can rearrange this equation to solve for n. The quantum number n is equal to the square root of 8ml squared times e divided by h squared. We have all the information we need. A cubic box whose side is 10 centimeters long has a volume of 1 liter. So we can take the length of our box as 10 centimeters or 0.1 meter. The mass of a helium atom is 4 atomic mass units, or 6.64 times 10 to the negative 27 kilograms. The energy of the atom is given as 6.2 times 10 to the negative 21 joules. And Planck's constant is 6.63 times 10 to the negative 34 joules second. Plugging in all these numbers gives us the value of n. It's 2.7 times 10 to the 9th, or 2.7 billion. Here's the probability density function for n equals 20. Remember that there will be n minus 1 nodes between x equals 0 and x equals L. This means 19 nodes, and there are 20 locations where the probability density is at a maximum. Now imagine what the probability density function would look like if n is 2.7 billion. Imagine dividing a 10 centimeter length into 2.7 billion sections. These would be very small sections. The probability density would be at a maximum in the center of each of these sections. You can see that the variations in the probability of locating the particle in the box becomes undetectable. We can say that quantum mechanics essentially agrees with classical mechanics in this case. In general, we could say that quantum effects, or divergence from classical behavior, occurs when we're close to the ground state. Remember that a very large number of nodes means a very highly excited state.